Hello again, everyone. Last time we took an in-depth look at exponents, and today we will be discussing radicals or roots. Just like subtraction is to addition and division is to multiplication, these radicals can be thought of as the inverse operations to exponents. Let's start by taking a look at the pieces. This symbol right here is what is referred to as the radical. The smaller number just in front of the radical is referred to as the index, and it's this number that indicates what kind of root we will be taking. Meanwhile, the number or expression inside the radical is referred to as the radicand. What these radicals or roots tell us to do is to find the number that when multiplied by itself the index number of times, or raised to the index power, gives us the number inside of the radical. To demonstrate, this third root of 27, or the cube root of 27, is asking us to find what cubed will give us 27. At this point, we must realize that 27 is 3 cubed, which means the cube root of 27 is that 3. Let's consider some more examples. When we have a radical such as this one that doesn't have an index written out in front of it, there's an implied index of 2, and we call this the square root. And this is asking us what number squared will give us 16. It's at this point we must realize that 16 is just 4 squared, so our answer here is just that 4. The square root of 16 is 4. We can consider any number root, and the thought process is the same. Consider now the fourth root of 16. We have to realize that 16 is 2 to the fourth power, which means our fourth root of 16 is just that 2. These radicals can actually be expressed as exponents as well. If we have the nth root of some number a, then we can write this as a to the 1 over n power. Because of this, evaluating radicals has the same rank as exponents in our order of operations. So when going through PEMDAS, radicals must be evaluated at the E stage for exponents. Writing radicals as exponents also shows that they will follow the same set of rules we went over last time. For example, now consider the nth root of a to the m power. Rewriting the n root as an exponent will give us a to the m now raised to the 1 over n power. The power rule of exponents says we must now multiply the two exponents together. This will end up giving us a to the m over n power. We can use this to go back and forth between exponential and radical notation. We can also see that radicals will distribute the same way as exponents. That is, they can distribute into multiplication and division, but not addition and subtraction. For multiplication, if we're taking the nth root of a multiplied by b, we will get the same thing as taking the nth root of each number individually and then multiplying together. For example, consider the square root of 9 multiplied by 4. First, evaluating with our order of operations, we will do the inside of the root first, treating the multiplication like it's in its own set of parentheses. 9 times 4 will give us 36, and we want to take the square root of that. We can write 36 as 6 squared, meaning the square root of 36 is just 6. If instead we split up the radical into the square root of 9 multiplied by the square root of 4, we'll have to write 9 as 3 squared, multiplied by 4 is 2 squared, which will give us the square root of 9 being 3, multiplied the square root of 4, which is 2, giving us again 6. We get the same answer, so the property holds true. Meanwhile, for division, we'll see that the nth root of a divided by b will give us the same result as taking the nth root of the a and b and then dividing. For an example, consider the square root of 100 divided by 25. Following our order of operations first, we'll have the square root of that division inside a set of parentheses, which will give 100 divided by 25 is 4. And the square root of 4 is just 2. On the other hand, if we break it up with our property here, we'll have the square root of 100 divided by the square root of 25. We can write 100 as 10 squared, and 25 is 5 squared. So taking the square root of 100 will just give 10, and the square root of 25 is just 5. So we get 10 over 5, which is just, again, 2. These answers match, and again, our property holds true. To show that radicals do not distribute across addition or subtraction, consider the square root of 16 plus 9 compared to just the square root of 16 plus the square root of 9. For the first one, we must do the addition inside the root first, which will give us the square root of 25, and the square root of 25 we saw was 5. For the second one, we've seen that the square root of 16 is 4, plus the square root of 9 is 3, and adding these, we get 7. These answers do not match, so radicals do not distribute into addition or subtraction. Before we wrap up with radicals, there are some important things to mention regarding simplifying radical expressions. We won't always be able to get a nice whole number from radicals. For example, the square root of 2. There's no nice whole number that when multiplied by itself gives 2. If you plug this into your calculator, you would get a number with a lot of decimals, but for an exact expression, we can't simplify this any further. There are cases, however, where we'll have a number that doesn't have a perfect square root, but can be factored with a perfect square. For example, consider the square root of 18. No nice whole number when squared will give 18, but we can check for any perfect squares that 18 will be factored into. These perfect squares include 2 squared, which is 4, 3 squared, which is 9, and so on. In this case, 18 can be split up into 2 times 9, where 9 is a perfect square. We've seen that these roots can distribute into multiplication, so we can split this up into the square root of 2 times the square root of 9. Now we know that the square root of 9 is 3, so for our answer, we get 3 times the square root of 2. We conventionally write any numbers multiplying a radical to the left of it, so we don't confuse it for a number inside of the radical. One more convention with radicals is that we don't like having them in the denominator. Whenever you end up with a radical in the denominator, the way to simplify it goes back to how we manipulate fractions by multiplying the numerator and the denominator by the same thing. In these cases, you want to multiply the top and bottom by the radical that is in your denominator. Let's try this on 1 over the square root of 5 and see what happens. Because we have a square root of 5 on our denominator, that will be what we multiplied the top and bottom by. Doing this on top will give us 1 times the square root of 5, and the square root of 5 times the square root of 5 on the bottom. On top, we're just left with the square root of 5, and on the bottom, it's the square root of 5 squared. Let's write the square root on the denominator as a 1/2 power, and use our power rule to see that these two exponents should multiply together, giving us the square root of 5 over 5 to the 2 over 2 power, which is just square root of 5 over 5 to the first power, which is just square root of 5 over 5. So you can see that by choosing to multiply the top and bottom by whatever root was on our denominator, we were able to get rid of that root on the denominator. There are often a few ways to approach radicals, especially when it comes to simplifying them, but we've laid out the essentials here to review. Until next time.